Hi, I'm Faisal Rahman from University of Karachi. I'm giving a talk on doing cosmology and investigating the CMB cold spot with the EMU survey. This is the agenda of the talk. You can contact me on my email always if you have any questions. So I'll just start quickly. EMU-ASKAP is going to be one of the most sensitive survey of its time before the launch of the square kilometer array. It will cover around 75% of the sky, and it will cover all the southern hemisphere up to plus 30 degrees declination. NVSS covered most the northern hemisphere, but EMU will be 45 times deeper, expected to be 45 times deeper. It will initially it was planned around 10 microgenskis RMS with estimated 70 million plus sources. However, now we are likely going to have 2 microgenskis and roughly 27 million sources, but it is still going to be the most sensitive survey of its time and will cover more sources. So a lot of good science potential for us. Yes, EMU-ASKAP has a planned resolution of around 10 arc seconds. So we'll first start with the integral and differential power law distributions. This is the differential power source power law distribution, and this is if we integrate it, we get the integral source count, which is basically the source count of all the sources above a certain minimum flux limit. For theoretical calculating it, we used ASCAD's extracurricular electric database S cubed, which is basically for 1.4 gigahertz sources. But if you want to calculate sources for particular fluxes, you can always play around with interpolation and stuff like that. So for sources between 50 microgenskis to 570 microgenskis, we get a differential source count of around slope values k and gamma around 57.24 and 2.18, which are published in Rahman 2015. Most of my talk is based on my 2019 paper written with Mr. Javed Iqbal, published in Astronomy Reports. And some of the discussion will be on CMB cold spot discussion will be from the enduring enigma of the cosmic cold spot, published in Physics World in February. If you are interested in there, you can read that. So in Kanda 2007, they used around 1 microgenskis minimum and 100 microgenskis maximum, and obtained around k is equals to 1000 and gamma 1.9. Calama 2000 measured k is equals to 8.23 and gamma 2.4. Similarly, Michel Condon estimated k 57 and gamma 2.2 is close to Rahman 2015 values. To obtain integral source count numbers, we limited upper flux limit as 1 Genskis to exclude the effect of nearby possible bright sources. These are the values we got for different flux ranges. This is the minimum 50 microgenskis range, which was basically done for as a 5 sigma for the initially planned 10 microgenskis per beam sensitivity of EMU-ASKAP, but that is now 5 sigma will now be at 100 if 20 microgensky is finalized. So and these are sources if we cover a depth of certain redshifts for different flux ranges. Of course, it's a big challenge in radio astronomy to estimate flux, but just in case, if we are able to have statistical redshifts and divide them into bins, we'll know if we are including certain redshift limits, you will get that much of that much sources. So a related concept is short noise. Short noise is basically required because we are converting a discrete quantity of galaxy counts into a continuum galaxy matter density field. We are using it as a count as a proxy for that. Short noise calculation help in statistically confining that. It is inversely proportional to the number of sources per radian. So we have this for different redshift ranges. Of course, if we go higher redshift with, and more sensitive surveys, will have lesser and lesser short noise contribution. This contribution is important for high multipole values, because where in cross correlation or autocorrelation, because this can short noise can dominate that region, values in that region, CL values in that region. This is the short noise for different distribution. We can see for more sensitive we have less short noise, for less sensitive we have higher short noise. For image, for as a science goal example, we are using integrated Saxwell effect, which is basically the blue shifting and red shifting, or the CMB photons, because of the distribution of the matter. So if we have more matter, then you are likely going to have slightly higher temperatures, because the source, the photon which will enter potential well when will gain some energy, and it will come out. If the universe is not expanding, it will lose some that all the energy gained. But if we have accelerated expansion of the universe, then the well will collapse earlier, and then it will come out earlier, and we will still gain some energy, retain some energy which we gained. And similarly, if it goes to the voids, it will have relatively colder temperatures because of the underdensities. And this is the theoretically since we cannot directly measure ISW effect from CMB maps, because overall amplitude is very small as compared to the rest of the signal. So now what we do is we cross correlate CMB maps with the galaxy over underdensity maps. This is theoretically we can calculate it in this way. This is the galaxy window function, and this is the temperature window function. Galaxy window function is dependent on things like survey measurements like bias or redshift distribution, dn over dz, and magnification bias. Magnification bias is dependent on the integral source count slopes. So we ignored magnification bias for signal to noise considerations here, but for overall cosmology parameter analysis, that will be that can play an important role depending on the survey distribution, and if the slope deviates significantly from one value, So, but for surveys like NVSS, where slope didn't deviate much from one, this doesn't play that much role. But still, for high sensitive surveys, this with if we have a very good redshift distribution information, we can estimate its effect on the cosmological parameters. For signal to noise ratio calculations, we can use CSGT over delta CSGT. It is given as here. We can see short noise is playing its part. For EMU-ASKAP 50 microjansky sources, we have this signal to noise ratio for different redshifts and multipole values going calculated up to 200, and redshift up to 5.8 of roughly around 4. So depending, of course, in actual survey redshift information will be a challenge, as I discussed earlier, but just in case if we include information, and then we can precisely get the idea of how much signal to noise ratio we have. Of course, if we consider short noise, then we will have slightly lesser values. This is without short noise, and this is with short noise consideration. If we take the difference, we get this, which becomes slightly significant if we are having very precise analysis. And signal to noise ratios are also dependent on the overall sky coverage. This is 0.05 and highest is 0.75. So that is something that's the benefit which large area sky surveys give for goals like ISW effect, similar as the case with other surveys depending on galaxy and matter density distributions. And the more area you cover, and the more deeper you go, you are going to get better signal to noise ratio results. That's the bottom line. EMU investigating the CMB cold spot. We have recently made this group within EMU collaboration. So we have a CMB cold spot observed by both Planck and WMAP on the CMB cosmic microwave background southern area, located at around hours 15 minutes 5 seconds right transition, and minus 19 degree 35 arc minute and 2 seconds 2 arc seconds declination. EMU's unprecedented depth and high resolution will give us a chance to deeply understand it, which is it is not previously understood by a lot of surveys. Even the leading candidates like ISW effect are not able to explain this phenomena. We can test a lot of things like using the cold spot area compared with other areas like ACF, autocorrelation function, cross correlation, redshift distribution, galaxy bias evolution, power loss for intelligence, different source counts. If we are measuring things like magnification bias, and which magnification bias discussion you can have Bianchini 2015 paper, and that's the galaxy window function is affected by magnification bias if we have the slope alpha deviating from 1 significantly. Otherwise, the distribution, the window function is only dependent on redshift distribution and bias distribution. So for analysis like the way I discussed, this doesn't play much part because alpha is close to 1, so this part becomes negligible. Yeah, so that is something which we things like these which we are going to explore. Some of the things which we are planning are ISW, the obvious one, and then using clustering, masses, absence or lower than usual presence of dark matter, and bias evolution, unusual bias evolution in the CMB region. So that is another idea, that maybe it's not the redshift distribution, it's unusual matter distribution or the absence of dark matter in most of the galaxies that might be causing unusual underdensities, which are causing this. Because in most of the ISW studies, we only consider count and then use biases on average basis. Maybe there are some unusual values present in this region that may be caused. The other thing is cosmological modeling. Maybe some of the assumptions related to flat lambda city or dynamic dark models you consider are not working there. So that will give us a chance to study some unusual cosmologies, and maybe there are some unusual structures like southernmost pole wall which are causing this effect, or there are some other structures or some other flow-like structures where matter is flowing between different regions, like it happens with great electron dipole repeller, or maybe some unusual power law that I discussed for magnification bias. Maybe there are some theoretical issues like deviation from isotropy, which is usually a consideration for large on large scale, and maybe some more exotic explanation. You can check the details on my more details in my article. Another thing is I want to discuss the EMU Pilot Survey. This is their homepage. I got this image from there. This is the Pilot Survey field. If we zoom in, we get this Pilot Survey area divided into 10 different subfields. So Pilot Survey has EMU is really basically two type of catalogs. Components is just a count of the blobs, and the islands, which is the basically some grouping of those blobs into some algorithms. So if we check the different source resolution criteria, they provide a very good idea that most of the sources in the component catalogs are behaving expectedly, especially in high or relatively higher flux ranges, or 10 sigma, 5 sigma flux range. They are doing a lot of great job. Flux peaks are generally equal or lower than the flux integrals. And then in the island catalogs, we had slightly bump in at lower flux ranges, maybe due to the way clustering, the source count is working in the island catalogs. There's some effect on it, but overall, from using the criteria given in the Radio Galaxy Zoo paper, still we have it in a very tolerable range. If you are using this criteria, where this flux peak to flux should be lower than this factor. And then we have integral source count power low slopes for component island. For component we have 0.847, and for island we have 0.77, which is slightly different because component has a lot of faint sources which might merge with other sources in the island catalog, so we get a slightly lesser low flux sources, and also the slopes is steeper in the component one. This is the differential slopes 2.03 in component if you consider the whole field, and then all the sources, all those sources, and then if we restrict between 250 and 500 microjenskis, we get this slightly less, 61.88, 1.88, yeah. And then for island we have 1.78 and 1.698. So for flux restricted area, there's a slight difference in the slopes from components catalog. As I discussed, component catalog has relatively steeper slopes, which is likely due to the island absorbing one or most components and merging them into a single. However, this means it can not only merge a single source with multiple components, but also multiple nearby sources as one island source. This is a big challenge of highly sensitive 2D surveys. EMU is developing another catalog, EMU-ASKAP, which will provide more valuable details like redshift, cross matching, classification, extra by analyzing other catalogs and survey images. So I also checked if we have a lot of bright sources like greater than or equal to 1 Jansky. So these are the sources, and there's a cycle of around half degrees, sources which are half degrees within the half degrees of those bright sources. This is within the EMU 10 field data. And then if we exclude them, then we get a very small difference in the slopes. This is for the island. We FGC that was around 0.778. There it's very half negligible difference. Maybe we still need to do work. Maybe the flux distribution. EMU's high resolution ensured that we don't have that much of effect for individual byte sources on a very large number of sources surrounding it. So that may be the cause. But still I must, this is something interesting to see. And then we have certain issues related to flux distribution. To see. And then we have some issues with spectral indices. We can see that some of the spectral indices are unusually high or low. So they are mostly in a low SNR region, or relatively low SNR region. For high, we don't have that much of problem. So that might be something, and not to do with the nature of the sources, but the SNR or the resolution of the sources. So we have, I have plotted them in against different scale tests. For example, peak flux to peak flux SNR and integrated flux SNR, and then yeah, and then against the criteria in the Galaxy Zoo paper, which is given in the references, you might check, and and against the flux to peak flux to integrated flux ratio, we can see that most of the sources which are in the meet the source resolution criteria properly have reasonable spectral indices. Mostly steep sources are for sources with higher peak flux than the integrated flux. So that is something, and most of these high spectral index sources are concentrated at lower flux ranges. So that is something related to the how the source identifier or source finding algorithm, or maybe ASCAP soft is recording fluxes and measuring spectral indices. That is something going to be interesting to investigate further. And EMU-ASKAP might look in the catalog, value-added catalog, which is going to come after some time of the initial data release paper, will address a lot of problems and will also give a lot of details like redshift, cross matching, classifications, etc. And it will use techniques like pattern recognition and machine learning algorithm to improve upon the analysis, and will use data from the other surveys for cross matching purposes. For more details for EMU Pilot and upcoming paper, you can check the upcoming paper of Ray Norris and Josh Marvell and the rest of the team. So that will be something of interest for people. Thank you. That's all from my side. If you have any question, please email me.